So we are talking about finding reaction orders of reactants. So if you've done your homework recently, hey there, you remember how this goes? If we have A plus B going to form C, the rate actually can mathematically be related to, actually, let's do it this way. A plus B going to form C. Okay, the rate law expression looks like this, where you guys in your homework were coming up with some rate law constant K's times the molar concentration of each of the reactants raised to the reaction orders. And we just kind of use MN, you know, and it would be O if there was another reactant, etc. But we said how you can determine these reaction orders just by inspection. Okay, you guys did or will do something like that. Well, now we need to talk about how you get to them if you didn't like double the concentration and use that little cheat sheet. Okay, we need to use, right now we're going to talk about the algebraic method, and then we're going to talk about the graphical method. But in order for the algebraic method to make more sense, we're actually going to be using logs. So here is the law of logs, or kind of excerpt of law of logs. These are natural logs, but log base 10 is in log. They behave the same way. Oh, you smell good, Alexis. And I used copies of these last Monday. Okay, so I'll kind of show you why we have to use logs here in a minute. So you have to use logs. I'll get to the chase. Actually, if you have an exponent you're trying to solve for, which is m or n in this case, using logs will make everything fall into place. I'll show you how that works. So here we have two reactants, Q and R, going to form products. It was run twice. And the cool thing, and they did this on purpose, you know, when you set up your series of experiments, you experimental design, make it so that you can actually understand your results. So notice on purpose, for the first two trials, and I think that's all their trials are. There are 3 trials, yeah. For both trials, we didn't vary the concentration of R. So guess what? That means that any changes we see in the rate, and we do see changes in the rate, they are all due to the effect of changing the molar concentration of Q. Okay? So we basically want to find what the reaction order of Q is. The law of logs is what I just gave you. Okay, so kind of the generic rate law expression would look like this. Rate is equal to the rate law constant K times the molar concentration of Q raised to its reaction order times the molar concentration of R raised to its reaction order. But in this particular case, the molar concentration of R stayed the same. So actually that was on purpose. All right, so now what you see is basically we ran it twice. We have experiment 1 and experiment 2. That's what these little subscripts are. So the rate for 2 is equal to K times molar concentration of Q for the second trial raised to the reaction order times the molar concentration of R for the second trial raised to its reaction order, etc. We do this all the time. What we're going to do basically, and I kind of got grayed out, but we are basically going to take rate 2 over rate 1. You could also do rate 1 over rate 2. But rate 2 divided by rate 1 is equal to this ratio over here. The K's are the same because it was done at the same temperature. That's the only time you get K's are different. Rate law constants are different. And guess what this term does? So actually, you're going to see it here in a minute. But can you see where these go away? They cancel out, right? And these cancel out because they're the same. So we can rewrite that, and it looks like this. It looks like magic, I know.
Why don't the M's cancel out?
The M's don't cancel out. Well, if you look back at the previous slide, the molar concentration of Q is different for the 2 experiments.
Oh, okay.
And it gets complicated because I'll tell you how we get to M. That's the whole point. The M's do not cancel out. If molar concentration Q is the same, then it would have canceled out. All right, so we get this. So again, we're going to have to introduce logs to get to that exponent M. That's it. So here's how we use logs to get to M. If you take the log of both sides, which is awesome, you can totally do that. Okay, that seems like an algebra thing to do. The next thing you're going to see is if you take the log of this, the Q2 over Q1 raised to a power, the cool thing, and you're going to see it here in a minute, is basically you can bring that log, you can bring that exponent out. Let's see. That would be like the third line under logarithms that I just gave you. If you look at this right-hand column, the third line down, the natural log of x to the n is equal to n times the natural log of x. Okay, so that's the one we're using. Now, if you're like me, I couldn't just spit out that log law, okay? But you know it exists now. So the beautiful thing is basically you flattened out, in a sense, that exponent, and now it's just multiplied, m multiplied times log of this ratio. So now it's just kind of hardcore, just algebra a little bit. So if we want to get this by itself, it seems like we could divide both sides by log of Q2 over Q1. Does that seem right? Yeah. So it's kind of fun. It's not too bad. Okay, so that's what you see here. We can get to the reaction order M. And so we can plug in numbers there. And if you go back to the slide that has the trial data for the rates, the log of rate 2 over rate 1 is the log of 0.0104 divided by 0.00668. Now notice one of the things I've done here is I'm not worried about units. It's kind of weird for me to say that. But I don't worry about units because they cancel each other out. Okay. And then in the denominator you have the log of Q2 over Q1. Molar concentration of Q2 over molar concentration of Q1. Now if you're like me, I have to do this a few times because logs are messy on my calculator. Okay. In fact, what you see here is I've just basically done the ratio and then take the log of it. Okay. So the ratio of the rate 2 over rate 1 is equal to 1.56. The ratio of Q2, molar concentration Q2 over Q1 is 1.25. Okay. I'm not real good with logs, but I eventually get around them. So if you would crunch this on your calculator, you would get a nice, pretty integer-ish 2. Okay? So that's the reaction order of Q. And that's what we were after. And like I said, I don't know my way around logs too much, but I know what you cannot do is take the log of the ratio 1.56 to 1.25. That does not work. That's not how logs do not allow you to do that. Okay. So let's take a look at 12 and 13, and I'll push these out there. Oops. Push these hints out there. I actually made these hints the other day for Monday, but we didn't get that far. There they are. All right. So this is 12, and okay, so you're supposed to come up with the overall rate law expression. Rate law expression is the same thing. So basically, you're going to have to go whole hog and ultimately come up with a value for K, come up with a reaction order for A and B. Okay, and so generically speaking, the rate would be equal to some rate law constant K times the molar concentration of each of the reactants raised to their individual reaction orders. Okay. So if we focus on experiment 1 and 2, Actually, that next one's easier. So this one you are going to have to, as far as I could tell, use the algebraic approach that we just did. You focus on 1 and 2. Notice the reason you do that is like we ran into just a minute ago, that B stays the same. So that makes your life a lot easier. So it's just similar to finding the reaction order for Q, finding the reaction order for A. Okay, and now, since you have the reaction order for A, now you focus on, let's say I have experiments 2 and 3. You could do 1 and 3, or 2 and 3, it's the same diff. But notice we need to choose something aside from 1 or 2. We need to choose 3 because we did change the molar concentration finally of B. Okay? So now you're going to have basically your M is already solved for in the first part. Okay? So you can actually plug in your M values. Your K's will cancel. You get the rates from here. Okay, so those are all numbers that you really know the value for. And you know, of course, the value for the molar concentration of B at 2 and 3. And you're solving for N, okay, which is concentration of B raised to the N power. Okay. So it's like what we did also. And then lastly, in order, since it asks for the overall rate law or rate law expression, to me you have to go back and find K. And you get to pick which trial you want. And like we've done before, now that you know M, okay, you know N, okay, pick, and you can pick any of the 3 trials or 3 experiments and plug in rate, molar concentrations, and solve for K. Your choice. So 13 gets a little easier. So if you look at 13, the cool thing about it is 1 and 2, we hold the molar concentration of NO constant. And notice that the cool thing about Cl2 is it's doubled. It's like, yay! Okay, and I looked in my notes, and yes, you can go ahead and look for either a doubling or a quadrupling in the reaction rate to know the reaction order of Cl2 based upon those 2 trials. Then we can focus on experiments 1 and 3, and again, it's kind of a convenient sort of thing. Notice that we double the NO concentration, and so we can look at what the effect of the rate is. Okay, look for a doubling or a quadrupling to get the reaction order of NO. Okay, so that's that. All right, so I'm pretty sure, and I feel a little bit bad, we are doing experiment 6 tomorrow, and I'm pretty sure that this is actually the method that you're going to use. Graphical approach to doing the calculations of tomorrow's experiment. So this is a graphical approach. All right, so we have 2 reactants going to form products. We know that the generic rate law expression looks like this. Obviously, we don't know the reaction order out of the box with regard to either reactants. Remember, you can only get M and N through experimentation. That's it. That's it. All right. So again, I'm going to kind of massage things to show you how we can do a graphical approach to get to M and N. So here's the deal. Again, you can take the natural log of both sides. That's cool. Doing the same thing to both sides. Now, one of the laws, let's see if we can find it on here, is if you have, it's the first one up there, okay? The natural log of x times y, the natural log of x times y is equal to the natural log of x plus the natural log of y. Okay, so that's basically what we have here. Okay, we have the natural log of a product. Okay, so we can split those out. Makes our life a little easier. So we're going to run some experiments, and actually this is what you're going to do tomorrow. And in the first set of experiments, let me go back to the equation. In the first set of experiments, we're going to hold B constant. And the second set of, and we're going to let A vary. So B is basically going to be There's no influence by changing the molar concentration of B because you don't change the molar concentration of B. Okay, you're going to vary A and get to its reaction order. And in the second set of experiments, we are going to go ahead and let this stay the same, and we're going to vary B to get its reaction order. So we're going to have to do kind of two sets of experiments. Okay, so as long as we hold B constant, then what I'm going to go ahead and do when I break it out into the natural log of the product is basically the sum of the individual natural logs, is I'm going to go ahead and just kind of put B with my rate log constant K, because I'm like, neither one of those are going to change. This is going to change. Well, when we talk about graphing information, we always look for something that's going to make a straight line. Y is equal to mx plus b, and we have it there, whether we recognize it or not. Oh, I guess we don't quite have it. Now we have y is equal to mx plus b. So we said one of the laws of logs that we applied actually just a minute ago is if you take the natural log of something raised to a power, it's equal to that power times the natural log of that something. All right. So we can actually make a cute little graph. I know it seems kind of strange, but we can run it at several concentrations of A, getting different rates, and it kind of reminds me of the Clausius-Clapeyron plot. Along the y-axis, we're going to take the natural log of rate, and along the x-axis, we're going to take the natural log of the molar concentration of A. It should have a, can't remember if it's a positive or negative slope. I should know this. I guess it must have a positive slope. It should have a positive slope, and the slope of that line, I know it's weird, m is equal to m, but this m is equal to the slope, and this m is the reaction order. Okay, so that slope, m is equal to the reaction order, in this case of A. That's a wonderful thing. So that, in a nutshell, is what we're going to do. Okay. And here's kind of some laws. These are actually just a few of the on the sheet that I gave you. Take the natural log of a product. It breaks it out into basically in the sum of the individual natural logs. You can say the natural log of something raised to a power is equal to that power times the natural log of that thing. Okay. Yep. So like I said, this is what you're going to be doing, ln of rate and ln of the concentration of the thing that you let vary. Slope is equal to reaction order. Did I go backwards? No. Oh, see what's different here? Okay. Our second set of experiments, we're going to go ahead and now hold A constant, so we'll put it over here. And that actually will allow us doing similar to, I wonder if it's on the next slide. Similarly, for our second set, when we let A constant and let B vary, we're going to put the ln of the molar concentration of B to the natural log of the rate. And your slope, in this case, was going to be to your reaction order of B. You feel some Logger Pro stuff coming on? Yes. Logger Pro is our friend. So once we have M and N, basically, then we can go ahead and pick a trial and substitute in rates and concentrations and M's and N's, and we can come up with K. Oh, wait a minute. No, there's a better way. I forgot about this. We can actually get to K graphically, too. Okay, so here's how this goes. For our last graph, we are actually going to plot along the x-axis. We're going to plug in for each trial the molar concentrations of everything raised to now their known reaction orders. Okay, that's going to be along your x-axis, and just regular rate, not natural log, but just regular rate along your y-axis. And the slope will be equal to K. I forgot about that. So down here, this is A raised to the M, which we know now. B raised to the N, which we know now. Again, it's going to be a positive slope along the y-axis. It's just going to be plain old rate. Okay, and your slope is equal to K. Let logger probe spit it out. Okay. So we'll look at some data and see what we think. So you're going to see two sets of 4 experiments, okay? And so the 2 reactants we have are NO and O2. And let's see, I can't remember. It must be coming up on the next slide. But just for kicks, remember your generic rate law expression is equal to some rate law constant, which we're going to find out graphically here in a minute, times the molar concentration of NO raised to its reaction order, times the molar concentration of O2 raised to its reaction order. Okay, so that's your generic rate law expression. We need to find M and N and K actually. Okay, so the first 4 looks like our O2 is going to stay the same. So NO is going to vary, so we can get to its reaction order for the first 4 trials. And then we're going to change it up, and we're going to vary O2 but hold NO constant. So here they are. Here's all 8 side by side. So you can see that these molar concentrations stayed the same, and these did for the second trial. So here we can get to M, and here we can get to, should have chose a different color. So here we can get to M, and here we can get to N. Here we go. Well, that was anticlimactic. Okay. So we're going to let Logger Pro do what it's good at. So you actually in Logger Pro can do the function, do the ln. You could either type ln quantity and then bring down a column, or there's a function called natural log of ln. All right, so here's the raw data for the first 4. Okay. So in order to make our plot, we need the natural log of rate, which I did a calculated column here, is the 3rd column. And then along the x-axis is going to be the natural log of the NO concentration. That's the last column. So those last 2 columns over there is what we're going to do to make this plot right here. Okay, so the 4 triangles is your data, the natural log of rate versus the natural log of the molar NO concentration. Okay, and remember, Logger Pro will go ahead and spit back under statistics. It will tell you what the slope is. So 1.99. You think it's close enough to 2? I do. Okay, so we said the slope of that then would be the reaction order of NO. That's the slope. The reaction order is 2. Okay, so this is going to be similar. Looking at the last 4 experiments, now where the O2 varied and the NO was held constant. Of course, we need 2 calculated columns. The natural log of the O2 going to go along the x-axis. The natural log of the rate going to go along the y-axis. So here's what that plot looks like with those 4 points. So you think the slope of 1.02 is close enough to 1? Reaction order of 1, exactly. So that's it. And that's what you're going to be doing tomorrow. It's wonderful. Okay. Oh, yeah, we're not quite done yet. See, I keep forgetting that last part. So we can get to K. Now we know what, notice we went ahead and put the reaction orders in that we came up with. Reaction order of NO is 2. The reaction order of O2 is 1. Right? So now we're ready to go ahead and look at all of the overall reaction order is 3. So now we're ready to go ahead and look at all 8 trials. This is where I think it's kind of strange, but maybe, maybe not. So we need to basically take this squared, okay, times this raised to the first power. Okay, we need to go ahead and, like you see the title over here, what this says is NO, because it's second reaction order, O2 raised to the first power for each of the 8 trials. Cool. So remember that along the y-axis, it's plain old rate now. Plain old rate, we have 8 little data points, okay, where we took the molar concentration of each reactant and each of the 2 reactants raised to the reaction order. That looks pretty straight. Correlation coefficient of 1.00. So our slope then, and we talked about what units of K would be if it was overall 0, overall first, or an overall second order. But this is overall third order, because if you take 2 plus 1, that's 3. So actually the units of K, in order to cancel out the units brought by molarity, are going to be inverse, so I can't remember. There we go. They would be liters squared per mole squared per time. I know it's kind of strange. But remember, if it's overall second reaction order, it's liters per mole per time. And now this is in 1 more, so liters squared per mole squared per time. Okay. So how do we get liters squared per mole squared per time? Well, sort of like this. If we know our rate needs to be moles per liter per time, in this case second, okay, whatever is here, which is going to be K, needs to cancel what is brought to the table by our second order NO and our first order O2. Okay, so what makes it right is that liters squared per mole squared per second. So if we go ahead and if these are the units of our K, I thought like that was a bug down there. I'm like, oh my gosh. So those are our units of our K. Notice how things cancel out. Liters squared will cancel out here. Oops, that's not right. Liters squared will cancel out here. Okay. Mole squared will cancel out here. Right? And we're left with units of moles per liter per second. So that's an overall reaction order of 3. Okay. There's no extra problem for that. Continuing on. So we still are on track to have your unit exam, your Unit 2 exam.
2 weeks from today, or tomorrow.
Right, 2 weeks from tomorrow. And honestly, the cool thing about that, I think it's cool for all of us, I think, is it's before spring break. It's right before spring break. So it's good not to, you know, I don't know. I don't like having to retain things and then be tested over it. Although your final in here is comprehensive, but still. Okay. So the last example with NO and O2 is a good one because we basically ran it 4 times, and then we switched up things and ran it 4 more times. Okay, so we had 8 runs. We're switching gears to 1 run. Okay, I'm going to show you actually how you get to the reaction orders, not by using initial rates, which is what we were doing, but by doing it once and looking at how the concentration of the reactant changes over time. So this is a different approach to get reaction orders. Doing 1 run and doing what we call time concentration data. So here's how this works. Okay. We know that the concentration of a reactant is going to decrease over time. But depending upon which reaction order it is, it will decrease differently. Okay. So it will look different. In fact, I'm going to kind of start a little pile up here. Oh, look. It's one of my little thingies. Okay. So we're going to focus again on zero order, first order, and second order. 3 different things that you plot and look for a straight line. And these different plots of your time concentration data, remember it's just one run, actually will kick out to you, hit you over the head what reaction order the reactant is. Oh, also, I keep forgetting about K. From that same plot that you determine what reaction order it is, you can pick off K from that same plot. You don't need 2 plots. All right. So we're going to go 0 first. So 0 order. And actually kind of what, and I might have to revisit this, but what I'm going to draw on the board here is a few little equations I'm going to jot down. Those will be available to you on your Unit 2 exam. So you don't have to memorize it. That's kind of nice. So we're starting with 0 order. All right. So if something's 0 order, it's kind of weird. Basically, the molar concentration of that reactant raised to the 0th power, which anything raised to the 0th power is 1. So actually, if it's 0 order, its molar concentration has no effect on the rate. Okay. So the rate is equal to K. Well, and I'll just go ahead and put this up here. Integration, basically using calculus and integrating that first statement, you come up with this relationship for 0 order. It's been so long since I had calculus, so don't even ask. For 0 order, okay, the molar concentration at any time of A minus the molar concentration of A, it was initially, remember these A zeros is the initial concentration, is equal to negative K and the time of interest. That's for 0 order. We might use that later. Okay. But we need to get it into something we can plot, and we can't plot that yet. If we go ahead and get the molar concentration of A by itself, it looks like this. And now we do have something that we can plot. So I'm going to go ahead and 0 order, maybe I'll even just write this down. Rearranging it, A is equal to negative KT plus the initial molar concentration of A. So it looks like this. We can go ahead and plot. For all of these, time is going to be along the x-axis. We're going to let time, dun, 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 dun. But in this case, to test for 0 order, we are actually just going to plot straight up the molar concentration of A. Okay. If we get, and it will have a negative slope, okay, if we get a straight line, I'm not looking for negative or positive slope. I'm looking to see if that line is straight. If that line is straight, and I've tried to draw it straight here, the slope, and I'll go ahead and spell it out so we don't confuse our M's. The slope will be equal to negative K. That's how that works. If you go ahead and plot the molar concentration of A versus time and it's not straight, it's not 0 order. All right? And it's funny, maybe not so funny, but of course, this term over here, you know, this is the y-intercept, okay? And the y-intercept, of course, would be your initial molar concentration. This would be your final time. All right, ready? That was one. Dot, 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 dot. If it is first order, things look a little bit different. And I'll show you the integrated equation here in a minute. So, first order or reaction order of 1, it's the same thing. All right? We go ahead and getting closer to something that we can plot. If it's first order, notice how I've drawn a box around this. So actually the thing with the red box, I'm going to draw over here. We have this relationship between actually the molar concentration of A at any time t and the initial concentration of A. So that's A naught, okay, is equal to negative KT. That's if it's first order. Can't plot that yet. But we can, that's going to come in handy later. Okay. Actually, this is something we can plot. I'm going to go ahead and write that one down too. The ln, just kind of rearranging it. One of the law of logs is if you have, we talked about a product, you can take the sum of the individual logs. If you have a ratio like this, like you saw in the previous slide, a ratio of excuse me, the log of a ratio, it breaks out and it's actually negative. It was here. Anyway, okay. A is equal to negative KT plus the natural log of the initial concentration of A. So, like this slide says then, what we have to plot now is along the y-axis, instead of the concentration of A, it's the natural log of the concentration of A. So ln of A along the y-axis. We still have time along the x-axis. We still have a negative slope. And again, that slope will give us K. Okay. So here the y-intercept is the natural log of the initial molar concentration of A. This is the final time. So the point here is if you plot the natural log of the molar concentration versus time, and if it's a straight line, then it's first order. And remember, maybe you don't remember, but we can actually use just to kind of judge whether it's straight or not, you can use the correlation coefficient. It should approach -1. So there's an example of that. And last but not least, last one we're going to do is second order. Okay. I'm running out of room. So second order, if we change see where the red box is. Okay, that's a good one for second order. We'll be using that later. And remember, second order means the reaction order is 2. Okay. So 1 over A minus 1 over the initial concentration of A is equal to KT. Something that we can plot is down there at the bottom. So actually, this form, we can plot the inverse of the molar concentration of A is equal to KT plus 1 over the initial concentration of A. So go ahead and I'll just do it on here. So again, we have time along the x-axis. Along the y-axis, we have 1 over the molar concentration of A. Okay, notice of the 3, this is the only one that will give you a positive slope. And if your line is straight, then you have successfully identified that it is second order. If it's not straight, it's not second order. So in here, the slope, since it's already positive, is equal to K. No negative K about it. So that's how that goes. And I will give you a copy of your equation sheet for Unit 2 before you take the test, so you'll know what you're you'll know what you're up against. So in this case, the y-intercept is the inverse, or 1 over the initial concentration of A. So let's do a problem, shall we? All right. So this gets a little tricky. There are ways around it. And I'm not going to get to that problem right now, but it's nice that there's only one reactant. Okay, if there's 2 reactants, things get a little more complicated. But this was run several times, at different molar concentrations of NO2, and we have the rates for them. Excuse me, darn it. What did I say that was wrong there? It was run once. What did I tell you at the beginning here? This was run once, one run, and basically we tracked the decrease in the molar concentration of NO2. Final answer. So here's the one run and the decrease in the concentration of NO2 over time. And we're going to do 3 plots, and they're going to look like the plots on here, and we're going to see which one's straight. And for the one that is straight, we're going to use the slope to get K. Okay, so we're going to make 3 plots. Which one's straight? Okay. So I bet we're all on the same page here. Just like we said, if this one is straight, okay, that means it's 0 order. If this one is straight, that means it's first order. And if this one is straight, it means it's second order. By the way, I didn't do this, and I had been doing this. So the generic rate law expression is rate is equal to rate law constant K, which we'll be able to get off the slope, times the molar concentration of NO2 raised to its reaction order, M. And we're solving for M, and we can pick K off of the plot. So here we go. Just let Logger Pro do the work, heavy lifting for you. So these first 2 columns, actually that's raw data. Basically, I don't know how raw it is, but yeah, we watched the decrease in the molar concentration of NO2 over time. And then these 2 are calculated. Okay, of course that green one, we're looking for the first order check, and the inverse of NO2, we're looking for the second order check, order check. So here they look like. Doesn't look like a straight line to me. This is for 0 order, so we know that because over here, not only isn't the title, but we just went with the molar concentration of NO2 over time. Not a straight line. Those A, B, and C there, that's actually having Logger Pro say, okay, it's not a straight line. What is your best fit? And so it came up with those. Also doesn't look like a straight line. Having Logger Pro do something other than a straight line fit, it comes up with these A, B, and C. But notice that we know that is for first order because it is the natural log of the molar concentration. And so we're hoping the last one's straight. Oh, that looks pretty straight. Okay. Again, you're looking for straightness or whatever. It would be your correlation coefficient approaching. For this one, a positive one. For those other 2 with a negative slope, it would be -1. Slow, ding, ding, ding. It's like second order wins out. And there is our K. Is that not wonderful or what? And here, actually, this did make the stuff we talked about. If the overall reaction order is second, then we said the units of K will need to be liters per mole per time. So, yay! Pretty good. So it was that third plot that got us. Okay. So what I'd like to do instead of covering this topic is we're going to hit this on Monday, but instead I want to look at the homework. So under, I think your homework slide says something about graphical analysis. Of course, it's Logger Pro. But if you're like, oh my gosh, Mrs. Snipes, are you serious? Well, the thing is, there's only one plot, but the 28 through 32 are questions about that plot. So I'll show you what it looks like. And I did not have time to, doctor this one up, but actually I just at least show you what it looks like and maybe add to this and post this. Okay, so here's your, this I guess will be your hint slide, or might take me a minute, but okay, first off, when it said that you need to use Logger Pro to plot, okay, plot 27, that's why. basically, notice that you have 3 sets of data. And these are different reactions. They are not the same chemical reaction. I think that kind of throws students off sometimes. They're different chemical reactions. The reactant A has different reaction orders. You're basically, not so surprising, is one of those is going to be 0, one of those is going to be first, one of those is going to be second. You're playing detective to a certain extent. When it says 27, it says which of these corresponds to 0, first, or second. If you want to go to Logger Pro and kind of play around with it and picture which plot you need to do for each of the data set and only give me that one, I'm cool with that. Do you know what I'm saying? That would be 3 plots then. Like, let's just say data set 1, you go ahead and do a 0 order and it fails, right? The molar concentration against time is not a straight line. Let's say for data set 1, you go ahead and do a 2nd order and it passes. Print that one out and submit it for your homework. And actually, print it out because it's going to help you answer your other questions later. Okay? Any questions about that? So that's what I would do. All right, 28 says, what is the value of the rate constant for the 0 order reaction? My point is if you printed it out, from Logger Pro, you have the slope. And the slope is equal to negative k. Okay, does that make sense? So actually your answer to 28 is basically done if you printed it out. Okay, now if you want to just kind of refer me to however you want to do that. 29, skip 29 for now because we're going to talk about, glad we had this conversation. We're going to talk about half-lives soon. 30, what is the approximate initial rate of the 2nd order reaction? You should be able to do that. My hint for 30 is, let's see, I'll put it down here. 30, I'm going to say focus on first 2 data points. Because rate changes over time. Okay, so for whatever one, and I don't know if it's 1, 2, or 3, but for whichever set of data you guys decide a 2nd order, look at just like the first, like the 0 to 25 seconds, look at the change in concentration and make that use that to make your rate. Rate is change in concentration over change in time. Let's see, 31, what is the approximate rate when time is equal to 75 seconds for each of them? So, let's see. Trying to decide. Don't worry about that one for now. Don't worry about that one. All right, 32. What is the approximate concentration remaining after 110 seconds? Yeah, I think you should be able to do this one. I like number 32. Okay, for 32, you're going to have to go back to 32, I'm going to say get from graphs. Okay, so for 32, basically, remember you're going to have a bunch of graphs that have, I don't want to say this, they all have time, and what's along the x-axis can depend upon which order you checked. Yep, so I guess to me, if you want to use your graph, you would go out to whatever is 110 seconds. Does this make sense? Whatever time is equal to 110 seconds before the end, okay? And you're going to go up here and see where it intersects with what this molar concentration is. Now, you're going to have to do a little bit of correction because it might be either A, if it's a 0 order, or the natural log of A, if it's a first order, or 1 over A with a different size slope if it's the 2nd order. So go ahead and do 32. You're going to have to revisit your graphs. 33, A plus B goes from C and D is 2nd order. 33, that's not assigned, is it?
No.
Okay.
33 is
33 got up there by accident. Sorry, guys. Okay. All right.